Hello everyone. In this last part of the videos on Knapsack problem, we'll learn approximation algorithm for Knapsack fully polynomial time approximation scheme. So let us quickly recap what is 0-1 Knapsack problem. In 0-1 Knapsack problem, we are given n items a1 to an. Each item ai has size si and profit pi, and we are given an integral capacity knapsack b, and we are assuming all size and profits are also integral. Our goal is to find a subset of items such that their total size is at most b and their total profit is maximized. In the last three videos, first we saw order nb times pseudo-polynomial time algorithm. Then we talked about another n square pmax, where pmax is the maximum profit item times pseudo-polynomial time exact algorithm. And then in the last part, we talked about approximation algorithm. And remember the definition of fully polynomial time approximation scheme. In fully polynomial time approximation scheme, it's a scheme. So there are multiple algorithms. Depending on an epsilon, we'll get one algorithm, A epsilon. And we have the property that the solution for all instance I, if I look at A epsilon I, which is the value of the solution returned by A epsilon on input I, is at most 1 plus epsilon times opt I, where opt I is the optimal solution on I. So it's for minimization problem. And for maximization problem, similarly, we can define that the definition of maximization problem approximation factor ratio is here. So if A epsilon I is greater than or equal to 1 by 1 plus epsilon times opt pi I or opt I, then we call it's a 1 plus epsilon approximation algorithm. So 1 plus or fully polynomial time approximation algorithm. So first of all, it is approximation algorithm, which is 1 plus epsilon factor, and second part is running time. So for fully polynomial time algorithm, we need the running time to be polynomial in the input size and 1 by epsilon both. So runtime typically n cube by epsilon square. So it is both polynomial in n and epsilon, 1 by epsilon. And we saw last time there are some examples of PTAS or EPTAS which have worse running time. They're still 1 plus epsilon approximation, but the runtime is worse. Now we talk about FPTAS for 0-1 knapsack problem. So in this problem, we already saw the second DP, which gave a order n square p time algorithm, where p is maximum profit item, maximum profit of an item. Now the issue is, this is in the DP, we create a table, and runtime was n square p, because there are n square p number of table entry, and for filling out each table entry, we needed a constant time. But the reason it's n square p is because there are n rows and there are possible profits. Opt is at most np, where p is the maximum profit item. So there was np number of entries, and p is a numeric data which has log p number of bits, so it's exponential time in terms of log p. So what we want is polynomial time. So what we want is, we don't want so many rows, which is exponential in terms of log p input, but some polynomial number in terms of n. So instead of n square p, we want to discretize this. Instead of so many rows, maybe for some rows, we kind of want to club them together. And by doing this, we might lose some information, we might not get optimal solution, but we still want a good approximation. And what we will show is, we'll discretize by factor k, let's say. So let's say if the profit is p, we divide by k and then round down. So that is kind of a bucketing. So think of it this way: this is the profit values and this is value of k. So if we divide by k, all these values become 0. And if we divide by k, all these values becomes 1. So all these are mapped to 1 and all these mapped to 0. So it's a discretization process. And we'll choose k to be something like here, epsilon p by n. And then we'll show two things. If we choose k to be like this, the runtime becomes polynomial in both n and 1 by epsilon. And second, we have to show, which is more important, why such k is useful. How this discretized DP can actually give you a solution which is close to the optimal solution. So first, let's go over the algorithm once more. So we are choosing just k to be this value, epsilon times p by n. And then we define profit of an item, profit prime. It's a new function from previous profit I by k, the bucketing, and then floor. So now number of possible values, distinct values are less. So now only instead of p, we have p by k floor possible values. And by choice of p by k, it is n by epsilon here. So runtime becomes n squared times p earlier. Now it is, instead of p, we are having this p by k, which is n by e. We are getting n cube by epsilon runtime. Now the most important part, why it works. Why the approximation guarantee is more than, let's say, 1 minus epsilon times opt. So first property, let's look at this, is that profit prime AI is more than profit AI by k minus 1. So remember, this is a floor function. We are rounding down. So if we don't round down, this value can only grow up. So that is just giving us this value. Sorry, I mean, if I'm rounding it down, then if I take this value and take minus 1, compared to that, profit I is anyway larger because it's a rounded down value of this, but then this is still more than profit AI by k plus minus 1. So that's the first definition from only rounded down property. Then we are summing it over all items which are there in opt. We don't know opt, but let's say it's just a theoretical proof. So assuming we know opt, we are trying to just summing over all opt, all items in opt. So this is the sum. And the sum will give us this is the profit prime of opt, which is greater than or equal to profit of opt by k minus opt, cardinality of opt. So this profit of opt is the optimal solution of the original problem and the profit we are getting from this. And this is the opt, the profit of the optimal solution. Same solution, but the values are now for the rounded down profit function, which is this function based on this value. Then we just do a multiplication by k and we get this property. And the cardinality of opt is at most the number of items, which is n. So we can replace opt by n and we can get this lower bound. So this part is fine. We got n equal to 1. Second part is, if we look at profit of algo, we claim it is more than k times profit prime of algo. The reason being, here it is rounded down. So this value is surely more than k times profit prime AI, just that property. And now we use the property that algo, the solution by our algorithm, is actually optimal for the function profit prime. Because the DP we wrote is optimal for this profit prime. We are running on profit prime, and for that DP is optimal. So for profit prime, algo is more than profit prime opt. Opt was optimal on profit function, but now we talk about profit prime function. And in profit prime function, algo is optimal, not opt. This is very critical. So once we have this property, then we have the rest. So then profit of algo is more than k times profit of opt prime. From here, we know it is more than profit opt minus nk. So we can write this. And then the definition of k was, it is epsilon p by n. So we just replace it. So nk is epsilon p. So next step is, we know that opt is more than p max. P max is a single item which can be packed in the knapsack and it has a maximum profit. So we just take the item, we already get opt. We already get some profit. So opt can only be larger or equal to that value. So we can write this, and that is giving us 1 minus epsilon times opt. So this shows, for this problem, we can get 1 minus epsilon opt approximation in runtime n cube by epsilon. So if I take it, let's say 1 by 1000, the runtime becomes 1000 times n cube. So as you get closer and closer to 0, 1, I mean, epsilon gets closer to 0 or the approximation factor gets closer to 1, the runtime explodes. But there is a trade-off between approximation factor and runtime. So depending on your need, whatever approximation factor is the factor that you need, you can set your running time accordingly. Or if you have a fixed running time, then you can set the best approximation factor following this relationship. And this was only the beginning of approximation algorithm FPTAS for Knapsack. There is a lot of follow-up works, and the present best is almost settled. From n cube by epsilon, now we have O tilde n plus 1 by epsilon square. And then there are multiple papers in stock 2024 which achieve the same result. One is by Zhao Mao, other one is by Chen, Lian, another Mao, and Zhang. So they both showed this algorithm, which is O tilde. That means it's hiding some polylogarithmic factor in terms of n and 1 by epsilon, and they can solve from this. This is improvement. But this is the recent result, but this also mentioned the sequence of results for the problem, where there was steady progress in last 20-30 years. And as I mentioned in the beginning of the video, knapsack problem is one of my favorite problems. And this knapsack shows a lot of my papers which appeared related to knapsack problem. So one particular problem which is my favorite is just a two-dimensional generalization of the problem called geometric knapsack. So I'll just briefly talk about the problem. So in this problem, the items are, instead of one-dimensional item, two-dimensional items. So they are rectangles, like these rectangles. And each rectangle is some integral height and integral width. Like 9 is the width here, 6 is the height, and the profit is $100. Similarly here, 7 is the width, 6 is height, and 95 is the profit. Now your goal is to, and also you're given a square knapsack, which is k cross k. Instead of one-dimensional knapsack, now you have a two-dimensional knapsack. And we are having a square knapsack. And the goal is to find a packing of all items which maximizes the profit, which is same as the knapsack problem. But the packing is slightly different now because we have two-dimensional items. So what we need is axis parallel packing like this. The rectangles are packed parallel to the axis or axis aligned, and they should not overlap. This is a valid packing, and there are multiple variants. You can allow rotation, you do not allow rotation. In this case, rotations are not allowed, so items are packed 90 here, and then 60 here, and 5 here. Now we cannot pack any more items because then it will be overlapping with some other items. And under this constraint, we want to maximize the profit. And this is a very common question in, let's say, packing, when you are shipping a container from one place to another place. Again, you have this three-dimensional or two-dimensional boxes or rectangles, and you want to pack them parallel to the surface for gravity reasons or whatever other reasons. And you want them not to overlap, and you want to maximize the amount of profit. So for this problem, actually, there is a DP-based 1.89 approximation that we have given. So I have a talk in Fox 2017 on this paper. The video is on the web page, also in the algorithm page. You can see. But this is like the 1D knapsack is quite simple DP. It's just one page, a two-page DP. But here it's quite involved. It's more than 60 pages of DP. There are a lot of intricate techniques which is needed to break the barrier of previous best approximation to approximation. In general, if you're interested in knapsack or two-dimensional knapsack or online knapsack or other variants, please feel free to email me. I'll be happy to talk about these problems in more detail. And for 2D knapsack, one of the big open question is if there is a FPTAS. I mean, we already saw FPTAS for 1D knapsack. And it is known that for this problem, we will not have a FPTAS, but a PTAS is still a possibility. So it's a big open question in approximation algorithm, whether there is a PTAS for geometric knapsack or not. Thank you.